So welcome all to our second day of our geometry and physics section. The first talk of the day is by Henrique Sayerp from Unicamp, whose talk is titled The Heterotic G2 System on Contact Calabi-Yau 7 Manifolds. Thanks for the talk, Henrique. You can start.
All right, thank you. I'll do 15 minutes. Is that okay?
Perfect.
I think it's, yeah. All right, and I should also, well, first of all, let me thank the organizers for the invitation. And I must also apologize, I will not be able to stay for the next two talks because it's a bit late here in Brazil, so I might have to leave soon after my talk. So I'm really sorry about that. In any event, so the talk is about the heterotic G2 system, which is a topic of interest to sort of theoretical physicists in this interface between geometry of 6 and 7 dimensional spaces and models for string theory. This talk is from a mathematical perspective, so I'll try and convey an idea of what the heterotic G2 system is in this framework of Schrödinger's systems, but I will not explain the physics behind it, right? I'll just explain the mathematical problem, the well-posed, I mean, a clear mathematical problem that underlines this topic. So, and I should mention that this is joint work with Jason Lotte. Right, so for this, so the heterotic G2 system is a system of relations between various types of degrees of freedom of various natures, which correspond to sort of geometric fields on the manifold, sort of tensor related information, but also gauge bundle and connections on a gauge bundle satisfying a number of constraints. So I should probably revise the gauge theoretic notions leading to the heterotic system, and then explain how these fit in together nicely in these real 7-dimensional spaces, which we call contact Calabi-Yau manifolds, and how indeed we're able to produce solutions in a certain sense over these spaces. So let's talk a little bit about just general notions of gauge theory, which will be relevant to us. So the topic is possibly most familiar to you from the perspective of 4-dimensional geometry and sort of 1980s huge progresses in the understanding of geometry for manifolds via the moduli space of anti-self dual instanton connections on vector bundles over a given Riemannian manifold. In this case, the sort of key notion is the notion of self-duality or anti-self duality with respect to the Hodge star induced by the Riemannian metric on two forms, and in particular the two-form part of the curvature f of a connection A on a gauge bundle over your manifold. And in this context, if you pose the L2 norm of curvature, also known as the Yang-Mills energy, as the action of interest, then its critical points are what's called instantons, and it's easy to see just by the Bianchi identity that solutions to this first equation, so-called anti-self-dual or self-dual, depending on the sign of the eigenvalue here, are both what's called Yang-Mills connections and critical points of the Yang-Mills energy. Now, in higher dimensions, particularly in string theory, if you want to consider base manifold, which has higher dimensions, then it's not even altogether clear what self-duality means, seeing as now the Hodge star maps two forms into n-2 forms. So this can only be made sense of in the presence of some additional structure. And that's sort of framework proposed by Donaldson, Thomas, and then deeply developed by Tian in a paper, Annals of Mathematics in the year 2000, where sort of high dimensional version of this theory is formulated in terms of an n-4 structure. So if you're given an n-4 form on your manifold, then relative to this form sigma, one can define instantons as eigenstates, as connections for which the composed operation of wedging with your additional structure and then taking the Hodge star, then has sort of evolutive role with an eigenvalue, which doesn't have to be plus or minus 1. It typically is -1 and then has a positive eigenvalue, which sort of depends on the context. Now, you can still pose, however, in any event, you can still pose the Yang-Mills functional, which is just an L2 norm of curvature connection on the bundle, and assess whether your instantons in this generalized sense are still Yang-Mills, meaning are they still critical points. Now, if your structure is not closed, then in general this will not be true. It might be in particular cases, and it will be in the particular case I'll present to you today, but it doesn't have to be the case. So typically one wants to pose that this n-4 form be closed, so that then similar argument by the Bianchi identity implies that instantons are Yang-Mills. The real condition really is that F lies in the kernel of D, with respect to exterior product, the kernel of D sigma. Now, of course, if D sigma is itself automatically in the kernel, that's we're going to see a non-trivial situation where this Yang-Mills phenomenon still occurs. Anyway, so classical examples are, Donaldson theory, where this sigma is really just the choice of orientation. Hermitian-Einstein connections in the Kähler setting, where you complete dimensions using multiples of the Kähler structure, Kähler form. G2 instantons on 7-dimensional manifolds, where the n-4 form is now a 3 form, which is precisely the so-called G2 structure, and in 8 real dimensions, similar situation where your n-4 form is now a so-called spin 7 structure. Now, in particular, we're going to be looking at the heterotic G2 system, as I told you, a relation between a bunch of geometric data on the manifold, together with some gauge information, some gauge field on an auxiliary gauge bundle. Now, let me tell you briefly what's a G2 structure manifold. So as I mentioned, a G2 structure is defined by a 3 form. You can think of it as a pointwise, smoothly varying pointwise vector cross products on the tangent space of a 7 manifold. It's only defined for 7 manifolds. And in this case, the vector cross product is indeed defined by a totally alternating 3 tensor. In particular, we can look at, these are called G2 structures, by the way, because G2 is the sort of stabilizer of this vector cross product. If you write it in terms of octonionic multiplication, the imaginary octonions, that's why it relates to the group G2, which is a 14-dimensional compact simple group. Now, a particularly interesting, particularly useful sort of decomposition among the differential forms in this context in terms of irreducible G2 representations. So at the level of 2 forms where the curvature is going to live, the form part of curvature is going to live, is so there's a copy of the Lie algebra of G2 sitting inside lambda 2 at each point, which is characterized by, as I told you, this minus eigenvalue. It's always there, and this would be our notion of instanton, right? So we'll declare instanton G2 instanton in this context as precisely where curvature lies in this component. And there's 2 ways to characterize it: as an eigenvalue situation, or a completely equivalent one, where wedging with the Hodge dual of phi, which is a full form, is 0. So this process of wedging with psi, the Hodge dual of phi, is can be seen as the projection onto the 7-dimensional complement of lambda 14 inside the total lambda 2, which has rank 21. And just the same, you have a 27-dimensional component of interest inside 3 forms. So now, as a geometric structure on a manifold, your 3-form phi has a well-defined torsion, and this torsion can be characterized by 4 components in each of these irreducible bits. And these are, in some sense, the sort of geometric information on the manifold that's called manifold K. Then the torsion, the total information about torsion can be computed from the derivative of the exterior derivative of your 3-form phi and the exterior derivative of its Hodge dual, which is the 4-form psi. And then you have a 0-dimensional component, so it's essentially a scalar, a sort of rank 1 component living in a rank 1, sort of a 1-form component, 3-form symmetric 3-form component, and then also a skew symmetric 14, in fact, rank 14 component, right? So together, and star 1 is repeated, it occurs twice. That's by the way, that's a theorem, and these completely encode the torsion of phi as a geometric structure, sort of reduction of the frame bundle, if you will. So now the degrees of freedom mobilized in the heterotic G2 system as posed by work by Eric Svanes, Xenia de la Osa, Magdalena Larfors, and in a number of works of the past sort of 5 to 6 years, consist in the following. So they set up the following request. One wants a bundle F, on which A of F denotes the space of smooth connections. So a G bundle, let's think of it as a vector bundle, in the heterotic T2 system or Hall-Strominger system would comprise of a scalar field, lambda, a dilaton field corresponding to a function mu, and a 3-form which is called the flux, the H flux. Now we have gauge fields, which would be a connection A on the bundle, on a bundle, say, we're going to call E, and a connection theta on the tangent bundle of K itself. So we need 2 gauge fields and 3 geometric fields satisfying a number of relations, right? So first of all, we expect both the connections, both the gauge fields to be G2 instantons on their own right. So they must wedge with psi, as I told you, give 0 so that they lie in the 14-dimensional irreducible subbundle of 2 forms. And moreover, the condition on the theta connection on the tangent bundle can be relaxed a little bit to be just orders of alpha prime, or alpha prime is called the string scale constant. So it doesn't have to be an instanton on the most. It would be great if it were, but the Strominger system is dramatically overdetermined as it is, so we need to use any freedom we can have to try and produce solutions. And indeed, the solution is going to show only satisfy the second instanton equation to orders of, indeed, in fact, you can choose them to satisfy this equation to very large orders of alpha prime. But in any case, physicists tell me that this is fine because they have a perturbative, that this fits into a perturbative argument in alpha prime, so only the sort of dominant terms in the end matter, and that's enough for the kind of physical argument that would ensue. So indeed, by packaging together all this information, here's the concrete mathematical problem posed by De La Osa, Larfors, and Eric Svanes in the series of papers. So we want a 7-manifold with a G2 structure 3-form phi, such that the torsion realizes these fields. So tau 0 really is the scalar field, tau 1 really is the gradient of the dilaton, tau 2 is 0, so this means that the G2 structure is called integrable. It's the integrability of the structure. And the flux can be constructed from the previous information in a definite manner in such a way that an anomaly-free condition, also referred to as the heterotic Bianchi identity, is satisfied. What it says is that relative to sort of global order of alpha prime, what happens is the Chern-Simons defect on the manifold between the characteristic classes associated to the gauge fields we're considering, even though they're gauge fields in different bundles, they are representatives in the Run cohomology, sort of representatives of their second Chern classes, do live on the manifold, and we ask that the Chern-Simons defect between the two is precisely the exterior derivative of the flux. So it's a 4 form, right? So we need to satisfy this equation 4, and this one has to be satisfied on the nose. Now, our solutions do exactly that. Are there any questions so far? Cool. Bruno, can you still hear me?
Hello, yes, I hear.
Okay, cool, all right. My connection is a bit hesitant, so if it might be interesting if you sort of interact at times, just so I know you guys.
Oh, okay, it's been running smooth so far.
If you can leave your camera on, maybe that would help. If you freeze for too long, then.
Okay.
All right, thank you. All right, so the next bit, I'm going to introduce these nice spaces, which we call Calabi-Yau links. These are Sazakian manifolds, so they're in fact regular Sazakian manifolds, so they are circle fibrations over Calabi-Yau 3 orbifolds, which can be obtained in a systematic way in large numbers by choosing weighted homogeneous polynomials and cutting out weighted homogeneous projective subvarieties in weighted CP4. So just to recall the information that's relevant for what for this narrative I just described. So we're dealing with some so contact geometry can be seen as an odd dimensional analog of symplectic geometry. So now we're in a situation where one form generating the fiber directions of the circle fibration is maximally non-integrable. And its exterior derivative, d eta, we can call it omega, and it behaves as a transverse symplectic form. Just the same way, Sazakian manifold is, it's a particular type of contact manifold in which you have a compatible Riemannian metric, a compatible transverse almost complex structure J, and which are compatible in a suitable way. And so Sazakian geometry can be seen as a sort of transverse scalar geometry, so sort of odd dimensional analog of transverse scalar. It's rigorously characterized by the fact that the metric cone over it is actually scalar, right? So we're in this setting where you are doing the sort of most intuitive next thing once you have a well-understood sort of Calabi-Yau geometry and you want to have a model in 7 dimensions, which is to take a very simple fibration over the well-understood situation, which emulates lots of the features which can be found in Calabi-Yau geometry. In particular, this very nice construction by Milner, if you consider in ambient space, in particular, let's think about C5, and you cut out a variety with an isolated singularity at the origin, then the link of the singularity over a sufficiently small sphere, in this case, let's think of S9, right? So I'm thinking about the n equals 4 situation. We'll cut out a 7-dimensional manifold, compact, smooth, 2-connected manifold K. And they have precisely the structure, and if you want, you can think of K as the restriction of the Hopf fibration of S9 over CP4 to a variety V, to a projective threefold inside CP4, and you can add weights to the situation in a comparatively easy manner just by minding your polynomials to be suitably weighted as well. In fact, we're in a situation where all the things in the game are called Milner. So we have the Milner fibration, which is sort of the complement of the link, is actually an open book decomposition, or sort of with binding S1. the typical preimage of an element there is called the Milnor fiber. The Milnor fiber, it can be seen as obtained from mu spheres Sn, where mu is called the Milnor number, and mu is also the dimension of the natural algebra obtained from the Jacobian ideal of this polynomial, and it's called the Milnor algebra. So all the things, the Milnor number is the dimension of Milnor algebra. And what's interesting in this case is that the topology of the Milnor fiber can be related in a sort of interesting way to the Milnor number. So it's a very beautiful theory. All in all, there's a lot of rich structure embedded there. We are not going to exploit much of this in a profound way, but I feel obliged to attribute credits to Milnor. Now, as I told you, we are considering the more general situation, let's say in C5, where a weighted C star action is now underway. This is, by the way, how Philip Candelas and collaborators generate the large list of Calabi-Yau 3 orbifolds in the sort of early 1990s. So we're in that same setup, but now we're looking at these polynomials, and as much as they define a link over an odd-dimensional ambient sphere, as opposed to just the singular Calabi-Yau manifolds, which they actually cut out as projective, weighted projective subvarieties of weighted CP4. And indeed, if given a suitably weighted polynomial, homogeneous polynomial, then the Milnor number can be related, can be obtained or computed directly from the polynomial data. In particular, if you choose your weights well, you can make sure that the first Chern class of your threefold is actually 0, thus making the base manifold, the base of the circle fibration, an actual Calabi-Yau 3 orbifold, and therefore the link contact manifold with transverse Calabi-Yau geometry. And the condition is really just this. For reference, if you choose the completely homogeneous situation, you're doing and you adopt, say, the Fermat quintic, then you can see that if all the weights are 1, the sum of all 5 weights is 5, and that's indeed what you get, Calabi-Yau quintic inside totally homogeneous CP4. That's just an instance. So this diagram sort of synthesizes what I've just told you. And so the link sits inside a local sphere around the isolated singularity of the polynomial. The sphere is a Hopf fibration over weighted CPN, and therefore the restriction, the link can be seen as the restriction of this Hopf fibration to a subvariety here. Right, so the link, the 7-dimensional manifold, is also circle fibration. This map is as nice as it could be. It's an orbifold Riemannian submersion. And therefore, we're feeling inclined to call these manifolds contact Calabi-Yaus, meaning contact manifolds with a transverse Calabi-Yau structure, meaning a transverse. So we have a transverse degree in terms of PQ Dolbeau language. In particular, we have a transverse sort of analog of a holomorphic volume form, which behaves just the same in the transverse directions. And the derivative of it says theta here, it should be eta, which is the contact structure. This will behave like the Kähler 1-1 form. And indeed, it relates to the real and imaginary parts of epsilon by a volume, sort of volume relation, completely analogous to the Kähler setting, right? And indeed, it can be shown by Habib and Vizzoni. Habib and Vizzoni has shown that every such Calabi-Yau link admits a S1 invariant contact Calabi-Yau structure as such. And therefore, we can sort of do Calabi-Yau geometry in 7 real dimensions. This is the situation, completely specialized to our case. Furthermore, now in the 7-dimensional situation where you're morally the product of a Calabi-Yau threefold by a circle, then you also have a natural G2 geometry. Again, please think of theta as eta, right? It's the contact structure. It's a typo reproduced here. Theta will be our geometric field, so it should absolutely not be confused. But in this case, we produce a G2 structure which is not torsion free, right? All its torsion is concentrated here, but it's what's called co-closed, so it's sort of not too bad. In particular, it's integrable, and as we will see, even though this G2 structure is not closed, it will have the property. These links have the property that G2 instanton connections are also Yang node. Well, here's a few examples. We could do many more. Never mind this quantity here on the right. It's called the Crowley-Nordstrom invariant of the G2 structure. It won't be of interest for us today, but you can get many, many examples performing nicely the way. So you can generate lots of examples. Choose to. Right. So let's address the issue then of specializing gauge theory to the Sazaki 7 manifold. Sorry, I wrote here, this is like transverse Hermitian Mills-Yang, but it should be Yang-Mills. I should only notice that later. In fact, there are three natural notions of instantons, right? Because if I give you an n-4 structure, that gives an associated notion of instanton, and there are three types of n-4 structures. One I can construct from the contact geometry, and then which does induce a notion of contact instantons. There's the business I can draw directly from the transverse scalar structure, which define transverse Hermitian Yang-Mills instantons. And then there's the sort of intrinsic G2 instanton actually. So we should specialize our gauge theory in a way where we understand what's natural to consider. This is some work I've done with my former student, Dr. Luis Portilla, where we look at the relation between these three types of instantons, and the sort of main takeaway lesson from here is that if you define a natural notion of transverse Hermitian Yang-Mills, which is just the literal transverse analog of what we had before, and if you define G2 instantons with respect to the G2 structure, then if moreover your Sazakian, so I should mention there's a good notion of Sazakian holomorphic bundles over such manifolds, right? You ask some sort of a compatibility between a transverse holomorphic structure on the manifold and on the fibers of a vector bundle. Then for Sazakian holomorphic bundles, if your base manifold is contact Calabi-Yau, then in some sense, and you restrict attention to Chern connections, meaning connections which are compatible with the Sazakian holomorphic structure and just sort of unitary, then with respect to some Hermitian metric on the fibers of the bundle, then essentially all three notions of instanton coincide. So among these sort of compatible connections, these Chern connections, all three notions of instanton coincide, which leaves us comfortable to proceed with just about any of them, but in some sense unifies this narrative before we can go on, since there's so much structure originally there. Right. So if we specialize all this language to our case at hand, our 7-dimensional case at hand, we can produce a G2 structure, but now with a little subtlety. I want to control the size, the scale of the circle fibers on my 7 manifold, right? So I want to call it epsilon. Epsilon should govern the size of the circle fibers, and I'll define a G2 structure accordingly. Right, so you can see if you compute the metric, the Riemannian metric, which is kind of induced by this G2 structure, you can see clearly that epsilon is the dimension of the fiber, right, along the sort of contact one form, and it doesn't really change the metric on the base, and similarly just scales the volume accordingly, right? So now thinking of a circle fibration where we get to choose the length of the fiber, this sort of diameter of the fiber. Now here's a big theorem saying everybody comes together nicely. So if you're given such a contact Calabi-Yau manifold, then given any string length, so given any alpha prime as small as you choose, there exists constants in such a way that the G2 structure I just told you is co-closed, it satisfies the torsion conditions, and indeed realizes the sort of geometric fields from its various constituent elements. Furthermore, if you pull back the Levi-Civita connection of from the Calabi-Yau, right? So Levi-Civita connection of a Calabi-Yau metric is itself a Hermitian-Yang-Mills instanton on the tangent bundle of the Calabi-Yau. So if you pull it back to our gauge bundle E, therefore, is the pullback of the tangent bundle of the Calabi-Yau to K, right? And by pulling back the Hermitian-Yang-Mills Levi-Civita connection of the Calabi-Yau metric, we automatically get a G2 instanton. This is an easy theorem to prove that pulling back instantons essentially still gives you an instanton. So this one is easy to cook. Our gauge field is an instanton. Moreover, we have a lot of degrees of freedom in this construction to generate a connection now on the tangent bundle of the total space of the 7-dimensional manifold, which is itself a G2 instanton to order at least alpha prime squared. And moreover, the data we obtained satisfies the heterotic Bianchi identity square on the nose, so we're in this called anomaly-free setting. And then we know quite a bit about the asymptotics of these parameters if you choose a regime where the string constant alpha prime is arbitrarily small. Are there any questions so far? You good to go? Now, yeah. So let's look at how this construction goes. But to be honest, I will skim through the actual proof. I don't want to bore you with the lengthy computations in terms of connections, their torsion, and the rest of it. I'll just give a general hint of how these solutions are obtained and how we managed to actually solve the system. So first of all, it's easy to compute the torsion of the G2 structure is given by these two conditions. In particular, it's what's called co-closed. And then we can compute that in the example I just told you over the contact Calabi-Yau. So essentially, the 4 components of torsion are obtained as such. In particular, since it's co-closed, then tau 1 and tau 2 are 0, so we only have tau 0 and tau 3, which means in particular that our torsion is totally symmetric. And the 3 form, the 3 flux, can be explicitly explained as well. If we compute, therefore, the prescribed Chern-Simons defect, which we want to impose between the gauge fields, then it's literally just a multiple of omega squared. And then this is the result, the easy result I told you. It's easy to obtain a G2 instanton on this pullback bundle just by pulling back the Calabi-Yau metric Levi-Civita connection itself. So this one is easy to arrange. So our gauge bundle in particular is a rank 6 bundle, right? Rank 3, complex rank 3 bundle. Furthermore, let's now specialize to sort of a Darboux, local Darboux coordinates, if you want, in the Sazakian sense. So E0 will be the vector field along the circle fibration, then E1, 2, 3, and their J's will be the transverse sort of Darboux frame in local coordinates, and describe everything in such a system. Then it's easy to express the Sazakian, the contact Calabi-Yau structure, the 2 form, the sort of transverse scalar and transverse holomorphic volume forms in terms of such a frame. And moreover, it's easy to compute the structure equations of this frame, which will give us a sort of first relation between, the goal here is to relate the sort of natural Levi-Civita connection on the 7 manifold and this pulled back connection A, right, which really comes from the Calabi-Yau. It really is the Levi-Civita connection of the Calabi-Yau base. So by looking at the structure equations, you can see that the connection matrix here can be expressed in terms of the original pullback connection A plus a sort of perturbation, which we call B, right? So this, you can see, these are 7 by 7 matrices, right? So the first row and column are 1 length, and then each of these are 3 by 3. These are 3x3 blocks. All right. So sorry about that. It's a slight abuse, but so long as we're clear, this is 1, 3, 3, right? 1, 3, 3, and similarly. So it can be found that if you pull back this sort of SU2 connection, if you want, right, it comes from the Calabi-Yau structure. So this is an SU2 connection from the base, which is a pullback, so it's trivial along the 7th dimension. Then the actual Levitsky connection of the natural G2 metric in the setting can be understood as a perturbation of such guy by something that depends on sort of all the available data. And I here is a central element in SU3, right? So I is just a sort of, minus II is just a central element. Now, since A has a holonomy in SU3, then sorry, did I say SU2? I meant SU3, right? So this is the fact that A is an SU3 connection, right? Let me also clarify the notation. So I really is the 3x3 identity. When I say E, I mean this multi-vector where it's triple vectors, E1, E2, just to make life easier, right, in these blocks. Now we have a lot of freedom here. For instance, we can exaggerate by a factor K this natural perturbation, which we just found from the structure equation. Can do that. And this has an interpretation as a sort of a, as if we were kind of squashing the metric. So, you know, it's a different connection that would correspond to a squashed metric on the 7 manifold. But that's just a curiosity for the time being. We have a lot more freedom though. There's more degrees of freedom naturally sitting there, and we're going to need all of the degrees of freedom to produce solutions. So if I call now curly I, the sort of central element I mentioned to you, right? This comes from SU3 sitting inside SO7 in this situation. And we denote by this bracket operation the sort of vector cross product matrix obtained from a triple. Now in this sort of elegant notation, we can express a particular element in this sort of connection type element C, which is just this complicated expression here. And by raising an index in the H flux, in the 3 form, we can see that C essentially realizes its torsion, right? Now, in the previous terms, therefore, we now have this guy C, right? This expression here, which is a natural degree of freedom in our context. And therefore, I can add another degree of freedom, essentially delta, which is new, right? We had K and epsilon, and now we have delta along C, which is yet a third degree of freedom in the setting. And then look at the connection, which has a torsion essentially determined by this combination of the transverse scalar structure and the actual index raised torsion H 3 form. Now, alas, we would hope that this connection could be a G2 instanton on the tangent bundle, but it can never be a G2 instanton. In fact, we can prove that it's never a G2 instanton. However, by fiddling a bit more with this connection, we can produce something which is almost an instanton. It's arbitrarily close to being an instanton, which is fine for perturbative theory. So here's what we do. We take this central element in the Lie algebra and just consider the tensor product with the vertical direction. We're essentially twisting the tangent bundle by a sort of hypothetical line bundle, right? That's essentially what we're doing. And well, this twist is expressed then by this sort of multiplicity M. And by performing this twist, what would amount to an actual twist, we do the connection that would be natural to a twist, but we can think of it as a connection in the original tangent bundle, just by adding multiplicity corresponding to the twist. And by doing that, well, now we're in good shape and can show that can always choose these parameters, these degrees of freedom, these 4 degrees of freedom, in such a way that this connection is almost G2 instanton to order of alpha prime. So if we define, what we find is that by defining these 3 quantities, lambda 1, 2, 3, in terms of these degrees of freedom in this sort of Kabbalistic way, well, first of all, we satisfy with these guys, we satisfy the heterotic Bianchi identity on the nose. So this is an anomaly-free theory, and my lambdas, the necessary relations between those lambda 1, 2, and 3s, in fact, can be satisfied so long as this funky combination is strictly positive and so large that alpha prime can be guaranteed to be positive. So they're in the sort of inverse relation. And then it turns out that one can always choose several combinations of these. In fact, satisfying causing the instanton equation to be satisfied to, in some sense, arbitrary orders of alpha prime. So here's one solution. There are many, right? These just so that you believe a lot of solutions can be obtained. So one can choose those parameters in such a manner. This is now just a simple exercise of just finding various combinations of parameters to solve the equation. And this is physically meaningful precisely when the length of the circle fibrations becomes small. So you can think of this regime really as an approximation of Calabi-Yau, of 6-dimensional Calabi-Yau geometry, but in 7 dimensions. It's sort of thickening of Calabi-Yau threefold into 7 dimensions, which is kind of interesting. Then there are other solutions with similar asymptotics, but exhibiting slightly different features, which I don't want to drag you through. But in any event, many more solutions are possible, or one can find solutions exhibiting several interesting features. Moreover, the nice asymptotics I just explained to you, as alpha prime is chosen to be small by the physical circumstance, they are a complete consequence of imposing the Bianchi identity. They are not ad hoc choices imposed on the ansatz. So this gives a notion that this suggests that formulating the problem in such a manner is in some way natural to the physics. Right? So furthermore, I mean, I can tell you a bit more about where this is going. This is what I want to explain. The preprint is available in my first transparency at the beginning of the video, and it's on the archive. Perhaps people might be interested in knowing that Jason and I, since then, have been considering an even stronger construction of actual solutions that satisfy the G2 structure, the G2 instanton equation on the nose completely, using a sort of a full Yau analog construction. So looking at some fibrations over K3 surface, and then using the sort of full Yau framework to construct the actual solutions to the heterotic G2 system. So this is work in progress, so I'm not announcing any results just now, but this is one of the avenues where sort of the models for heterotic string theory can be obtained. And for physicists in the audience, the whole motivation for this is that, as De Laos, as Svanes, and Lafers have shown, is that if provided with a solution to the heterotic G2 system, then one does obtain the correct sort of supersymmetric equations one would expect in heterotic string theory. So that's basically the motivation for this. And we've provided the machine that, at least to approximative order in the string scale, can mass produce examples of toy models and model spaces for this. Okay. All right. So thank you. This is probably a good place to stop. Any questions? All right.
Como faz essas mãozinhas ali? Então tá aplaudindo aqui. Como é que se põe essa mãozinha?
Ali embaixo tem corrections.
Eu não tô achando, mas não faz mal. Peraí, eu tenho uma pergunta.
Maybe you want to ask it in English?
Oh, sorry. Yes, it's late and I'm sleepy. Sorry. It's like 11. anyway, right. So do you have any idea how the space of all these almost G2 instantons or sort of quasi, how the space of such types of solutions compares to the space of G2 instantons itself? See, I ask because in the case of like the SU2 instantons or so, the usual guys in 4 dimensions, it's a big deal that you get connections which are close in a precise sense to be in an instanton. And then one knows that those connections that have this epsilon kind of extra behavior, that space of things which are nearby is homotopy equivalent to the space of instantons itself. So you retract it and you get an instanton. You don't know precisely what it is, but you know that it can be taken by a homotopy.
Right, it's a thickening of the moduli space.
Right,
The
so
approximate instantons, yeah.
So is that the same in your case? These approximate instantons,
Fair
do they also
question.
live in some space that's
Fair question. I have two answers to it. So first of all, in the immediate sense that sort of Ugo Bruzzo has
Sorry.
studied. Sorry, can you hear me?
It was a little bit broken up, but yes, please continue.
Okay, so there's two answers to your question. So in the immediate sense that you're asking, is there an analog of Ugo and Beatrice's study of approximate instantons in this case? Not yet. So it might be interesting to just, and then it's not really a question about the Strominger system, right? It's really a question about possible thickenings of G2 instanton moduli space by these approximate instantons, right? How much can we know about them? One caveat, though, which I should make clear from the start, is that G2 instantons are an elliptic theory in this generalized setting as well. So since the manifold is odd dimensional this time, you would expect the moduli space of G2 instantons to be a bunch of points. So its expected dimension is 0. Not to say that this is a completely understood thing. In fact, to even understand the moduli space of G2 instantons is an ongoing, very hard problem. In particular, the compactification of G2 instanton moduli space is very hard, and it's in a very meaningful way still an open problem. The formation of singularities, for instance, is for fixed energy, say, or bubbling. I mean, all of it is very complicated. So I should say this from the outset, but no, we don't know anything. I don't know that anyone has studied approximate G2 instantons from the perspective of thickenings that you suggested. And it might be, I think it would be interesting to do it. So
I mean, actually much older stuff, right? The original Taub's construction was already like that. The instanton patching that he did in the differential geometric setting, he already did it that way. So he added some epsilon curvature and then deformed it by homotopy to the space of instantons. So it's quite old. But anyway, it could be that it would be nice actually if it happens in your case, because then you don't have to work very hard to actually get the specific instanton. You already know that there are limits that will give you instantons, G2 instantons in this case.
That's a fair point.
Anyway,
I mean, constructing G2 instantons on their own, is not that hard. What's hard is construct G2 instantons that work as gauge fields for the Strominger system, right? So, in fact, that's the second answer I'd like to give to your question, which is now not the question you asked, but a question that looks a lot like the one you asked, which is the following.
I said a nicer one. Okay, good.
Yeah. So Erik Svanes and his collaborators, so Xenia and Magdalena, have also shown that if you want to understand now thinking about the moduli space of solutions to the Strominger system, right, to the whole system, it has a nice description. I mean, in terms of deformation complexes, you have a nice linearization of its tangent space, and it can compute its dimension and all the rest of it. So long as all this data you obtain from the Strominger system can be combined into a connection on a much larger bundle, which is the sum of essentially all the bundles in this picture, plus some endomorphisms and maps from one to the other and the rest of it. in such a way that you obtain a G2 instanton on that much larger bundle. That's the condition you actually need, right? So if you want to be able to write a deformation complex for all of these data, this corresponds to finding this is going to work. And you're going to have sort of expected dimension and ellipticity, maybe in some sense, so long as all of this data produces a G2 instanton on this much larger bundle. So then you may say, what happens since our approximate instantons are not instantons? Well, it doesn't help, as you see, because when you get to, you need a deformation complex, it doesn't help it to be, your middle cohomology, for instance, or your H1, it doesn't help that you're almost zero. You have to either, you're either zero or your complex is not really working, it's not really a complex. And then we checked. In fact, a student of mine, Enrique Lazari, has visited the UK, visited Jason, visited Norway, and they computed this together. And it turns out that our approximate, our solutions to the heterotic system, together with containing these approximate instantons, does not quite give a G2 instanton on the larger bundle. So we can't fully compute the sort of physical invariance the sort of geometric invariance you'd expect to be of interest to physics from this. This is an absolutely new discovery, right? This is something we learned last month, and which motivates us to construct this other solution I'm sort of working towards, emulating Fuyao, which in this case would define sort of larger G2 instanton on the larger Q bundle square on the nose. So this is very much the sort of where the state of the art lies in this business. We don't want it to be an approximate.
I see. So there's a lot of fun to be had on action yet.
Yeah, there's
All
stuff
right,
to
thank
compute. There's fun. It's mostly fun for students, right? Because once you explain what needs to be done, then students learn quite a bit actually computing stuff,
Right.
serving a higher purpose, right? Yeah, but so this is definitely where the discussion is going. If we can find a better example, then we can actually compute the linearization of the moduli space of solutions to the Strominger system, larger system, and that's meaningful for string theorists looking at these heterotic theories.
Great.
When we meet again in Argentina, I can tell you more about this over lunch.
All right. That'll be fun.
Cool. Thanks for the question.
Welcome. Thank you for the talk.
All right. So Bruno, how do you want to do this? Are we good?
What?
Are we good?
Yes. Are there any more questions? If not, let's please thank Enrique again. Thank you, Enrique, for the talk, for participating in our section.
Cheers. And I am very sorry I'm going to have to go because I have a family commitment just now. So, Adrian, but I've already seen Adrian's talk, so it's fine.
It's fine. Thank you. Thank you.
Yeah. Cheers. Hi, Adrian, and bye.
Hola, hola Enrique. Hello, everyone.
Nos vemos.
Nos
Perdóname,
vemos
tengo que ir.
en Córdoba.
Adiós.
Hasta luego.
Hola, buenas noches.
¿Qué tal?
¿Qué tal?
¿Puedo compartir mi the PDF?
Sorry?
I try to share my screen.
Oh, we can see it now.
Can you see it?
Yes, yes.
Okay.
We still have 1 minute.
Okay.
I found out that Alexandre, which is the next speaker, is also at a different section. So he may, for the next talk, maybe he will be a couple of minutes late.
Okay.
Just I'll wait until. Yeah.
It's a little blurry for me. I don't know for you guys. Adrian, can you just put more light or less light? A little bit change of. I don't know. I see it blurry. Not very clear.
I
For me, it's
really
okay. I don't know.
I don't know what to do. It moves.
Funny. That page is better. Maybe it was just the type of letter. Okay, this is clear.
Okay.
Okay, this is all right.
Okay, good.
The first one somehow it's very yeah, this was it was funny. And the next one was fine, no worry.
Okay.
Maybe it was just the type of letters in the first one.
I don't know what happened.
It's okay.
Yeah. Okay, thanks.
I guess we can start.
Okay.
So the next talk of today is by Adriana Andrada from Universidad Nacional de Córdoba, and whose talk is titled On Non-Kähler Complex Manifolds with Trivial Canonical Bundle. Thank you for your talk, Adriana. You can start.
Okay. Well, thank you very much, Bruno, and all the organizers of the session for inviting me to give a talk here. This is a joint work in part with Marcos Origlia and Alejandro Tolcacher, both from Córdoba. And well, you can interrupt anytime when you have a question. Okay. This talk will talk about some complex manifolds which will not be Kähler, but which have trivial canonical bundle, because these have attracted a lot of interest lately in the complex geometry world. So I review briefly the contents. We will remind a little bit about this canonical bundle of complex manifolds, and then we will move to the objects of our study, which will be mainly in two different settings. One will be in complex nil manifolds and solved manifolds, equipped mainly with locally conformally Kähler metrics. Is in this part here. And the second part of the talk, we will talk about complex manifolds which are obtained from almost contact manifolds, and which are related with the manifolds that Henriquez has talked about recently, about the contact Calabi-Yau manifolds. We will try to generalize that concept to the non-metric setting. So I will begin with the basic stuff. in any smooth manifold, if we have M a smooth manifold, an almost complex structure on M is a tensor of an endomorphism of the tangent bundle whose square is the minus identity endomorphism at any point of the manifold. This implies that the dimension of the manifold has to be even, and there are special almost complex structures which we will talk about now. If this almost complex structure satisfies this relation here, this one, this is called the Najenois tensor. Najenois is a 1-2 tensor defined in terms of the complex structure and the Lie bracket of the manifold. If this tensor vanishes identically on the manifold, then we will say that J is integrable, or it is simply complex structure on the manifold. Why is this important? Why this is called this way? Because of the famous Nylander-Nirenberg theorem, which states the following: if a real manifold of even dimension admits an integrable, almost complex structure, then M is a complex manifold. That is, there is an atlas of holomorphic charts with holomorphic transition functions. So a complex manifold is the same as a real manifold equipped with one of these integrable almost complex structures. So we can work either with the holomorphic charts or with the real charts plus this tensor. Any of these complex manifolds admit a compatible Riemannian metric, compatible in the next sense. A Riemannian metric is called Hermitian or almost Hermitian if the structure is almost complex, if the almost complex structure J is orthogonal with respect to the metric, or equivalently, it is skew-symmetric. It's the same, these two conditions are the same because J squared is minus the identity. And then, in this case, using this the skew-symmetry, we can define this omega like the combination of G and J, and it is a two-form on M, which is called the fundamental form of this Hermitian manifold, or almost Hermitian manifold. Well, as I said, any complex manifold admits Riemannian metrics which are compatible, Hermitian metrics, and many of them, indeed. But so the idea is to try to find one of them which is nicer or better than the others. And there is one very famous structure which receives the following name. It's we have the Keller manifolds, which are given by, it is a Hermitian manifold. I mean, when J is integrable, and this is Keller if the fundamental to form omega is closed. Remember, the fundamental to form is given by this. It is always non-degenerate because J is a isomorphism. So in particular, this is a symplectic form on the manifold. Well, but it is stronger than symplectic. It is given by this Hermitian structure. In particular, when we have that, it can be proved that the complex structure is parallel with respect to the Levi-Civita connection of the Riemannian metric. And when we have that, when we have this structure which is parallel, this induces a reduction of the holonomy, and therefore it can be seen that the holonomy or the Riemannian holonomy of M is contained in UN, where 2n is the real dimension of the manifold. Okay. So, well, but inside UN, there is a special subgroup, SUN, which also appears in the list of possible holonomy groups in the list given by Berger. So there are some manifolds which satisfy this condition, holonomy included in SUN, and in this talk we will call these Calabi-Yau manifolds. There are several definitions of Calabi-Yau manifolds. Some are stronger, some ask an equality here, not only included but equal to. But here we will use this definition. There are several inequivalent definitions, but this one will do for purposes. And in particular, when we have this, the metric is always Ricci flat. We assume from now on compact for simplicity. And it can be seen that this condition can be replaced or is equivalent to these two conditions together. One is being Keller. This means that the holonomy is inside UN, and also that there is what we could say a complex volume form. There exists a form tau, which is of type N0, which is closed, and this is the same as holomorphic because it's a top form, and is nowhere vanishing. This different from zero is nowhere vanishing. But if we note, we will try to understand a little bit better this condition here, and note that this condition does not depend on the metric, on the Riemannian metric. The Riemannian metric appears here in condition 1, not on 2. It only depends on the complex structure. So we can analyze that condition on any complex manifold. We will do next this. Okay. So if we take any complex manifold with a complex dimension n, its canonical bundle is a complex line bundle, which is defined as follows. Km is the nth exterior power of the holomorphic cotangent bundle of the manifold. This is a holomorphic vector bundle over the complex manifold M. And as usual, a complex line bundle is trivial if we can find a nowhere vanishing section defined on the whole manifold. So this is the condition. This is holomorphically trivial if and only if there exists a nowhere vanishing holomorphic N0 form defined on the manifold. So this condition here, the second one, means that the canonical bundle of the manifold M is trivial. So in particular, this is what is written here. Galavier manifolds are compact Keller manifolds with trivial canonical bundle. But compact complex manifolds with trivial canonical bundle, and which are not necessarily Keller or Calabi-Yau, have appeared in many instances in mathematics and theoretical physics now. So it's nice to have more results about these manifolds, and here in this talk we will try to provide some new examples, basically. Some known results about these manifolds. What happens in the complex dimension 2, a compact complex surface with holomorphically trivial canonical bundle is isomorphic to a torus or a K3 surface or a primary Kodaira surface. Those are the only possibilities. This one here, well, the first two are Keller, but this is not Keller. So it's a complex manifold with trivial canonical bundle, but not Calabi-Yau. What else? If we take, for instance, a hyperkeller manifold, which is a generalization of the K3 surfaces, and with that, this is that we have a Riemannian metric together with three compatible complex structures which anti-commute. There is an action of the quaternions on the tangent bundle of M. Then if we fix one complex structure, let's say I, M together with I, this complex manifold has trivial canonical bundle. Because we can take this form, complex form, omega I, which is the sum omega j plus I omega k, where these are the fundamental forms defined in terms of the metric G and the complex structure J and K. Well, and if we take this and we raise it to the nth power, we obtain a trivializing section of the canonical bundle. Okay. So those are, but there are some examples of complex manifolds which do not have trivial canonical bundle. For instance, these famous Calabi-Ekman manifolds, which are simply the product of two odd-dimensional spheres. It can be seen that these have that the canonical bundle here is not trivial. And Tosati, some years ago, has proved that a compact complex manifold has trivial canonical bundle if and only if it admits a Hermitian metric whose Chern connection has holonomic contained in SUN. So this relates the triviality to the existence of a special metric. This special metric is quite hard to find indeed, because it's the solution of certain differential equations, but you know that it exists. Maybe it's not easy to find. The Chern connection is a connection which leaves parallel both the metric and the complex structure, and its torsion is of type, is of type 2-0.
Adrian, sorry, I'm confused. For the case of the product of the odd spheres, I don't quite understand the canonical bundle. I know canonical bundles only for complex stuff.
Oh, this is
How is it?
this has a complex J. This is a complex structure, a complex manifold.
Mm.
I will talk about that a little bit later. When you have the product of two normal, almost complex manifolds, when you have two of these and you multiply them, you can construct there an integrable, almost complex structure, always.
Why is it integrable? Sorry.
Yes, yes. And this is also,
Why?
in fact, it's a homogeneous complex manifold, which can be seen. And it has been proved, I don't remember by who, that the canonical one, there is no nowhere vanishing holomorphic and zero form here in this manifold for that J. It's okay.
Almost complex. Okay, why it's integrable? I don't know, but you can explain later to me, I guess.
Okay. I will talk about that later a bit further.
Okay.
I don't remember now how can you prove that it is not trivial, the canonical bundle, but I will show you at least that it is complex. Okay, so these are some known results about these cases. And there is also another big family of complex manifolds which have a trivial canonical bundle, and it is given by complex nil manifolds. So I will talk about this a little bit. These are things that we study a lot in Córdoba, Hermitian and complex geometry of Lie groups, where the structures are invariant, and then that structure descends to any quotient by discrete subgroups. So we have this is a machinery to produce many examples. So I will recall that an manifold is a compact quotient of G divided by gamma, where G is a simply connected nilpotently group, and gamma is a co-compact discrete subgroup of G, a lattice. Not every nilpotently group has lattices, but many of them have. That happens if and only if the Lie algebra of G has rational structure constants for some basis. It is also known that the RAM cohomology of the nil manifold is isomorphic to the cohomology of the Lie algebra. This is a theorem by Nomizu. And moreover, these manifolds are parallelizable and aspherical, and fundamental group is isomorphic to the lattice gamma. A complex structure on this Lie group, nilpotent or not, is left invariant if the left translations are all holomorphic. And when we have that property, we can work at this complex structure is determined by what happens at the identity. So it is the same as working with the Lie algebra, an endomorphism of the Lie algebra, whose square is minus identity, and the Nye noise vanishes for the elements in the Lie algebra. And this left invariant complex structure induces another one called invariant also in the quotient, such that the projection is a local by holomorphism. And Barberis, Doty, and Verbitsky in 2009, they proved that there always exists a nowhere vanishing left invariant holomorphic N0 form on a nilpotent Lie group with a left invariant complex structure. And this implies that any complex Nil manifold with this induced complex structure has trivial canonical boundary for any lattice that we take there. So there are here a lot of examples of complex manifold with trivial canonical boundary. And they are also non-Keller, because it was proved by Benson and Gordon in the 80s that a Nil manifold does not admit Keller structures, either invariant or not, unless it is a torus. So if you take a non-abelian nilpotent Lie group, you won't get a Keller manifold. But there is a natural generalization of the Nil manifolds, which are called solved manifolds, which are the same, but simply replacing G nilpotent, and we take it now to be solvable. So if G is a simply connected and solvable Lie group, and gamma is a lattice that is a co-compact discrete subgroup, then the quotient is called a solved manifold. There are some shared properties with Nil manifolds, but there are others that are lost. Well, but some facts are the following. If G has a lattice, then it has to be unimodular. The trace of the adjoint operators is always 0 in the algebra. This is the same as before. The fundamental group is isomorphic to the lattice. All the other groups of homotopy are 0. And well, if two solved manifolds have fundamental, isomorphic fundamental groups, then in fact they are diffeomorphic. This is a very strong result of Mostor. But there is a problem here, is that we do not know whether a given Lie group has lattices or not. It is not easy to determine that. So it has to be done case by case, and it is not always easy to do it, and it involves a lot of number theory. But in any case, we can define complex solved manifolds in the same way as Nil manifolds. We can take an invariant complex structure, and then we induce, it descends to a complex structure on the complex, on the quotient, on the solved manifold. But there are differences. There are some non-toral solved manifolds which admit Keller structures. In this case, the metric has to be flat. It is a finite quotient of a torus. And there exist complex solved manifolds with non-trivial canonical boundary. This is different from the Nil manifolds, which they always have trivial canonical boundary. So, well, for instance, Fino, Otal, Ugarte, recently they were able to determine all unimodular six-dimensional solvable non-nilpotent Lie groups which admit a left invariant complex structure with a left invariant nowhere vanishing holomorphic 304. So all the associated submanifolds to these Lie groups have trivial canonical bundle. But it was not easy to obtain that classification. They used some particular results of exactly these dimensions, and they used some results by hitching on 3 forms on 6-dimensional vector spaces. But it was not easy to determine. One example, if this is in dimension 4, we take an extension of the Heisenberg 3-dimensional Lie algebra. This E0, where we have E1, E2 is E3, this bracket. E0 acts on H3 using this matrix. This is a derivation. We can consider a complex structure which sends E0 to E3 and E1 to E2. It is integrable. The corresponding Lie group has this form of a semi-direct product, and it has many lattices. Among them, we can find one which is called gamma 1, which is a 2-pi z times a certain lattice in Heisenberg, and gamma 2 is pi z semi-direct product with the same lattice in Heisenberg. In fact, this one, since we have 2 pi here, is in fact a direct product. And we can see that this quotient G divided by gamma 1, in fact, is isomorphic as complex manifold to a nil manifold. Yeah, this is a primary codide surface, and it is known that it has trivial canonical bundle. But if we divide G by gamma 2, we obtain a secondary codide surface which has not trivial, which doesn't have trivial canonical bundle. So the property of having a trivial canonical bundle does not depend only on the Lie group and the complex structure, but also depends on the lattice that we are using. So it is delicate to determine whether a submanifold has a trivial canonical bundle or not. But the problem here is that in this case, it's that there is a trivializing section of the canonical bundle which is not invariant. So it's more difficult to work in this case, but we will find some examples which we can assure that they are have trivial canonical bundle. We will find for now, in what follows, I will show you that there are certain submanifolds equipped with locally conformally Keller metrics which do have trivial canonical bundle. First, one definition that probably you all know: the Hermitian manifold is called locally conformally Keller if there exists an open cover of M and there are smooth functions on each open set such that the conformal metric on each subset is Keller. So I multiply G by this function on this open set I, and we have this new metric is Keller. So this is exactly what the name locally conformally Keller means. Locally, you can obtain a conformal, make a conformal change of the metric as so as to obtain a Keller metric. There is a simpler way to describing this, because this condition, it can be seen equivalent to having this, that the differential of the fundamental to form is equal to one closed Lie form omega, this is closed, theta, this is called the Lie form, and it satisfies this. D the omega is theta times omega. There is an expression a particular expression for theta, which is given in terms of the codifferential of omega. This theta is formed by the differentials of all these functions fi. They can be seen to glue together on overlapping open subsets of this UI, and then they form this closed, globally defined one-form theta. Well, this one is globally conformally Keller, and what the name says, the metric is globally conformal to a Keller metric. But we're interested in strict LCK metrics, which are not globally, because if it's globally conformally Keller, we know a lot about it because actually it's Keller. So we know about their topology, their Betti numbers. So we want to produce the other ones, which are really locally conformally to a metric. But it is easy to see that when the Hermitian manifold is globally conformally Keller if and only if theta is exact. So if we have LCK and on a simply connected manifold, then we have globally conformally Keller. So we don't want this. We need manifolds which are not simply connected. An example is given by this. If we take Cn and Cn, we take the minus the 0, and we consider homotheties by a complex number of length different from 1, we multiply, we send z to lambda z, we can divide Cn minus 0 by the group generated by this map. This is a complex manifold, and it is called a Hopf manifold. And it can be seen that it is diffeomorphic to a product of two dimensional spheres. One of them is S1. It's S1 times S2n minus 1. And the complex structure of Cn minus 0 descends to the quotient. So this is a complex manifold. Its first Betti number is 1, so it cannot be Keller. And if we take the usual Hermitian metric on Cn, but minus 0, and we divide it by c squared, norm of c squared, then this metric is also invariant by this map here, and it descends to the quotient. And it can be seen that this Hermitian structure on the Hopf manifold is LCK. And the Lie form is exactly d theta. Theta is the coordinate on the S1. So these are very nice examples of
Adrian,
yes, please.
Question. But if you take one that is globally conformally Keller, can't you just like remove a point or remove something and get a locally conformally Keller one? I mean, artificially make
but
it
the same function makes it globally conformally Keller.
No, but you make it not simply connected anymore. Oh, you
No,
mean
but you still have the function defined on the rest of the manifold, and you can multiply G by this function and makes it Keller.
Ah, okay. It's just,
Yeah.
I was thinking a reciprocal that doesn't.
No,
make
not
sense. All right,
always
thank
like
you.
that, but yes, we need some surely non-simply connected manifold, but maybe a non-simply connected manifold can be globally conformally Keller.
Okay, got it. All right,
Okay.
thank you.
Okay. So this is a very nice example of LCK manifold, but this one has an extra property. In this example, the Lie form, the theta, which is parallel with respect to the Levi-Civita connection. This doesn't happen always for the LCK manifolds. And they receive a special name. They are called Weismann, because Weismann was the first to work with this. It's an Weismann manifold, it's an LCK manifold where the Lie form is parallel with respect to the Levi-Civita connection. And if A denotes the vector field which is dual to the Lie form, then the Hermitian structure is Weismann if and only if A is Killing. So this is easy to establish. And there are some properties which are important, which hold only for Weismann metrics. For instance, the first Betti number of a Weismann manifold is odd, and there are strong relations with the Sasakian manifolds. I will not go into that, but yes, there are strong links with Sasakian geometry. So we will try to find a left invariant LCK or Weismann structures on Lie groups. In this case, this means that everything is left invariant, the Hermitian metric. Also, this implies that the Lie form and the fundamental to form are also left invariant. So we can work everything at the Lie algebra level. And also, if the Lie group admits a lattice, then this induces an invariant LCK or Weismann structure on the quotient. And this will be strict. It will not be global because the fundamental to form of the solved manifold is exactly gamma, the lattice. So it is not trivial. There are some known results about this. For instance, if the manifold is we have a Lie algebra which is LCK, then it cannot be semi-simple. If it is reductive and LCK, then it has to be, it only occurs in 4 dimensions, U2 and GL2R. If it is nilpotent and LCK, there is only one possibility, is R times the Heisenberg Lie algebra, and it is Weismann. And there are some other results of classifications dimension 4, but I will not speak much about that. But I will talk what we did with the former student of mine, Marcos Origlia. We studied the Weismann condition on solvable Lie groups, and we were able to describe their structure quite well because it's not necessary to understand everything that happens here, but if we take a Lie algebra, a solvable Lie algebra with the Weismann metric, and the Lie algebra is also unimodular, then this G can be written as a semi-direct product of the A is the dual to the Lie form theta, and this part here is exactly the curl of theta, this part here, and this also can be written as a central extension of a Keller manifold, of a Keller Lie algebra, and the Keller Lie algebra has a flat metric. So, and the action of A on this part here is well understood. If we restrict D to, or add A to K, to this Keller Lie algebra, is skew-symmetric and commutes with J. That is, it lives in the unitary group. I don't want to explain everything here, but we know how to describe exactly the Lie algebras which are solvable, unimodular, and have a Weismann structure. This is quite precise because also we can go in the other direction. If we begin with the Keller flat Lie algebra together with the derivation, which is in unitary, then we can produce a unimodular solvable Lie algebra with the Weismann structure, something like that. Well, and there are many examples of this. We have a lot of examples, and many of them have lattices. The question now is, let me see, one of these examples of manifolds equipped with one of these invariant Weismann structures can admit a can have the trivial canonical bundle, and we were able to obtain this. We can use this characterization to show that some of these Weismann manifolds have holomorphically trivial canonical bundle. Remember, G can be written as this, quite specific. It's a central extension of a Keller-Flat Lie algebra, and then we perform a semi-direct product where this one is the dual of the Lie form. And if we recall, this D was here in U of K, but in fact, we have that at A lives in the unitary group of the whole Lie algebra. And we were able to prove that a solved manifold with the invariant Weismann structure admits an invariant, nowhere vanishing, holomorphic N0 form if and only if this operator A, which lives used in UG, lives now in SU, has a zero trace, complex zero trace. And also K admits a holomorphic n-0 is my n-1 zero form. So this could be understood as a Calabi-Yau Lie algebra, a Lie algebra endowed with the Calabi-Yau structure. And we have this invariant. This means that M has holomorphically trivial canonical bundle. So, and well, we can produce examples because we have a way to construct this kind of Lie algebras, the Lie algebras with the Calabi-Yau structure, and we can understand also how to construct these derivations. And then if we perform these two operations, the central extension first, and then the semi-direct product, we obtain a Weismann. And if there are lattices, we obtain a solved manifold, which is invariant Weismann structures, and holomorphically trivial canonical bundle. So, well, this is quite algebraic, but I hope that you were able to follow the idea at least. So we can produce many of these examples, well, always when we can find lattice, which is not so easy. For instance, in dimension 4, in our construction gives all of them, and the only one that have trivial canonical bundles are primary Kodaira surfaces, which are nil manifolds. And there are some manifolds which give the secondary Kodaira surfaces, and they do not have trivial canonical bundle. And then we can produce many examples in higher dimensions when the Keller-Flat Lie algebra is exactly the abelian one. When we do the central extension, we obtain the Heisenberg. And then we can act on the Heisenberg with the exterior element with this matrix, where the first one is the element which is J of A, and all the other parts are given in a basis E1 to En, E to N, which give with these relations. E odd with E even gives the JA, and J sends the odd to the even part. And it can be seen that when all these numbers, real numbers, are integers, the manifold, the group has lattices. And when the sum is 0, it is exactly when it has trivial canonical bundle. So we have there a lot of examples. Okay, so this is the first part of the talk I wanted to talk about. So I'm moving to another setting, not in the Lie group setting, but well, the Lie groups will appear also. But we will show how to construct complex manifolds beginning with almost contact manifolds. And we will see when these complex manifolds have trivial canonical bundle. It will not be a complete characterization. We will only give some sufficient conditions, but they are by no means necessary. So I recall with the very basic definition, an almost contact structure on a odd dimensional manifold is a triple phi, psi, eta, where phi is an endomorphism of the tangent bundle, psi is a vector field, eta is in one form, and they satisfy the following. Phi squared is minus the identity plus this part, which involves the eta and psi, and eta in evaluated in psi gives the constant function 1. Well, these are quite, can be seen that it is natural to ask for this condition. I will show in a minute what it means. This implies that phi evaluated in psi is 0, and eta composed with phi is also 0. This means simply the following, that at any point, we can decompose the tangent space. We have x here, here we have psi x, and here we have the image of phi x. And then we can decompose at any point the tangent space as the part generated by psi, and the image of phi, which coincides with the kernel of eta. Yes. And in this part, the complement of this psi, phi acts as a complex structure. Phi is a complex structure on that subspace in the complementary distribution to the line bundle generated by psi. So it's a quite natural way to try to extend the notion of almost complex manifold to the odd dimensional case. But there is also a certain way to say that this phi is, that this phi is integrable, but I don't know why here we don't use the word integrable, but it is changed by normal. An almost contact structure is said normal if this tensor now is identically 0. This tensor and phi is given by this bracket of phi with phi plus this term, where this bracket is given by this. This is something similar to the Navier-Noise tensor of the complex structure. And this, in fact, is related to the Navier-Noise tensor of a complex structure. In fact, we can do the following. Here, we multiply m times r. This adds an extra dimension, so we have dimension even now. And we can define there an almost complex structure J. How? In this way, is stated here. J on this part, on the image of phi, is the same as phi. But then it sends, J sends psi to the usual vector field on the real line. So we extend, we add this other term, and then we extend the phi with this relation to the whole product manifold. Yeah. And this, and the normality of the almost contact structure is exactly equivalent to the integrability of this complex, almost complex structure. So that's why this received this name, and they are special. They are nice almost contact structures. And then we want to understand when this new manifold has trivial canonical bundle, because this is when M is normal. When this is normal, this means that J is integrable, so we can talk about the canonical bundle. And we're going to give some sufficient conditions. If we have an almost contact manifold, we will say that a K-form alpha on the manifold is basic if contracted with the vector psi is 0 and the Lie derivative of alpha in the direction of psi is also 0. So there are forms that do not depend at all on the vector field psi. They live on the other part, on the transversal part. If we denote by this form omega kb the space of all the basic forms, it can be seen that the derivative, the exterior derivative, preserves this complex, and when it is normal, then the endomorphism phi acts on basic forms and gives us back another basic form. The action is the usual one. So when we have that, since we have this, we can complexify everything and we can decompose the complex basic forms in types, PQ types, as usual in the complex manifolds. And then using this, we can show when, in example, some cases when the complex manifold n times r has trivial canonical bundle. The condition is this: if we take a normal almost contact manifold and then assume that there exists a closed lower vanishing basic form which satisfies this relation, wedge sigma, which is the basic form, wedge with the derivative of eta, the eta is the one form which have in the beginning, is 0. In this case, it is easy to see that this manifold, this complex manifold has holomorphically trivial canonical bundle. It is complex because this one is normal. And then we didn't know how to call this. We say that an almost contact manifold satisfying those two conditions here, those in color, they will be called of CY type. We didn't know what name to put them, so CY by Calabi-Yau, obviously. And this clearly is related to what Enrique talked about, because one clear example of this kind of manifolds are normal almost contact manifolds admitting the basic form sigma and with d eta equal to 0, because normal, there exists sigma. And if d eta is 0, then this is satisfied trivially. So, and here, well, I will not talk about that because it is kind of late. So, but we have here some examples. We can produce many examples of this with Lie groups, and we can find lattices. So we have compact examples of these manifolds. I will not go into that. But here we have also the contact Calabi-Yau manifolds that Enrique talked about recently in the other talk. We recall a contact Calabi-Yau manifold is a normal almost contact manifold together with a compatible Riemannian matrix satisfying this condition, and these other two. The first one is that the derivative of eta is 2 times phi, where phi is the two form defined in the same way as in the complex manifold. We contract G with phi. Phi is skew-symmetric using this. Well, a manifold which admits this kind of structure is called Sasakian. That's Sasaki. But if there exists also a closed nowhere vanishing form of N0 type satisfying this condition for certain constant Cn, then it is called contact Calabi-Yau. And there are examples in nil manifolds, and also with these Calabi-Yau links that were mentioned in Henrique's talk, and they have relations with G2 geometry in dimension 7. Well, it is easy to see that if we have this, all this, then contact Calabi-Yau manifolds are of Calabi-Yau type. It is very easy to check that. So we have there more examples of this kind of manifolds. And to finish, I will talk about the Morimoto's construction of complex manifold, which is related to the Calabi-Ekman manifolds with the product of two spheres. It goes like this. If we have two almost contact manifolds, then we can define on the product another almost complex structure. Let me try to make a drawing. We have the first one with psi 1 here, and here we have phi 1. And there is the other manifold which has its own psi 2, and here we have phi 2. And we multiply them. How do we define a complex structure here? Well, the natural way is to define like this. The complex structure on this part coincides with phi 1. On this part coincides with phi 2. And then the only other possible way to complete this is to send psi 1 to psi 2 with the j. J2, no, j, only j. So that is the way of defining a natural, almost complex structure on the product manifold. I guess this is the formula, the correct formula, but that is the idea. It's phi on this part, it's phi 1 in this part, phi 2 on this part, and sends psi 1 to psi 2. And Morimoto proved that he studied the integrability of this almost complex structure, and he showed that this induced almost complex structure on the product is integrable if and only if both almost contact structures are normal. So here, using that, the example is that it is already known that the odd dimensional spheres with the round metrics admit the Sasakian structure. In particular, Sasakian is normal. So when you take the product of these two manifolds, then you can construct an almost complex structure in this way, and this complex structure will be integrable because both of them are normal. So that is not the way that was discovered, the complex structure there. Calabi-Ekman did it before. This is like a generalization made by Morimoto. But then we can ask again when the canonical bundle of this complex manifold is trivial, and it's easy to see that when we begin with two of these, which are both almost contact manifolds of CY type, then this manifold has trivial canonical bundle, and it is, well, it's easy to see with all the information here. We produce this complex form on the product. These are the projections, and then we can verify that everything holds. It's the right N0 form. It is nowhere vanishing, and with all the conditions we had before, we can see that this is indeed closed and therefore holomorphic. And then this tau is a trivializing section of this bundle. well, and I will skip that part because it is kind of late and it's not so related. So thank you very much for your attention.
Thank you, Adrian. Does anyone have any questions? I guess Elizabeth will ask something.
No, I will ask when I will be in Argentina. Now it's too late.
Okay.
Okay.
I really enjoyed
okay.
it, but I don't think I can ask correctly even.
Okay, don't worry.
But I really enjoyed the talk though, so thank you.
Okay, well, thank you, Elizabeth. And we are looking forward to meeting you here.
Okay, thank you very much, Adrian.
Okay, thank you. I will stop sharing. Okay.
Nice, thank you. Next, we have Alexandre Santana. Alexandre is here, right?
His name is here, but here I don't know.
Yes.
Mystery. A gente vai ganhar por WO.
Alexandre is here.
Where?
He's in the chat, text chat. Okay. He's fixing the sound.
Elizabeth, where are you now? In Italy?
Yes, in Italy.
And what time is it? Midnight? Maybe.
Midnight. That's why I tell you, it's not possible to make coherent questions anymore.
Okay.
Also, but I was paying attention to the product of spheres story, so I understood a little bit, I think.
Okay.
But,
Well, great.
Yeah. Yeah, see, we tried to change the time, right? But they didn't allow us, the COMCA organization stuff. So very good.
I see. And when are you coming back?
First I go to Argentina and then I go to Chile.
You go directly from Italy, you come here and then to Chile. Okay, good.
That's right. It's a packing nightmare because you see it's like 40 degrees in Europe. Anyway. So, but it's okay.
But it won't be very cold here in September.
I certainly hope not.
No.
Cadê o Alexandre?
Ele não estava saindo áudio para ele. Ele não conseguia. Eu acho que ele ouvia, ele só não conseguia falar.
Mas se ele sumiu.
Ele saiu, ele vai dar um.
Ele vai entrar de
reboot,
novo.
Né?
Não entendi. Que zoada. Então, Adriana, eu nunca tinha visto essas coisas, esses produtos. Depois, enquanto você falou, eu procurei um pouquinho na internet, eu achei uns textos falando dos produtos de esferas ímpares. Tem coisas.
Okay, now it's working.
Perfect.
Bom dia já, né? Porque já passou meia-noite.
Boa noite, Elizabeth. Aqui já está de noite também. let me share the screen. I think that we can see this.
Yes.
Okay. Okay. I am ready.
But we see like
I can
parts.
start.
Yes, yes, you're ready, right? Okay.
Yes.
So the last talk of the day is by Alexandre Santana from State University of Maringá, Brazil, whose talk is titled Control Sets for Bilinear and Affine Control Systems on Rn. Thank you, Alexandre. You can start.
Thank you very much. I'm very happy with this opportunity to talk about this work here and to see the colleagues and friends from Chile and some other places. So in this talk, I will present some geometric idea about this result, because I think that in this session, geometric session, the more important thing here in this work is to present the geometric idea. So this is a joint work with Professor Fritz Colonio and my student Juliana Sett. And the idea of this work is to study this control system here, number one, study this control, okay, right on, this control system here, and to relate the controllability properties of this control system with the controllability property of its homogeneous part. Homogeneous part is this one here. I mean, we disconsider this vector A and this vector B. So let me explain better this context. Here, this system is given by matrix A and Bi. So here is matrix in n times n, and the vectors, this small b here, small b1, and so on, are vectors in Euclidean space Rn. And the controls that we consider have values in the subset of Rn. So what we want to discuss here is the controllability properties. That means if you take, for example, in R2, let me consider here R2. So I am considering this system here restrict to two-dimensional Euclidean space. Then the important question in this work is to know if it's possible to find the controls U, this map here, such that the solution, the concatenation of the solutions of the system here can take some endpoint here and leave this point in another point Y in R2. In other words, we ask if it's possible to find the controls U such that for every 2 points that we choose in this Euclidean space, we can go from this point to this point here using the concatenation of the solutions of the system. For example, if you consider just the ordinary equation AX, then we have that in this case here, the dynamics of the solution it's not controllable. I mean, if you choose the initial value here, then we have the solution or trajectory of this ordinary differential equations here, and we cannot control this trajectory. We just fix some initial point, and then we have a copy of this trajectory. Now, we can put here some map U and another matrix B, multiplying this vector X, and then we will have this new system. For every fixed U, we will have our ordinary equation, because if you fix U, then we just have A equal A plus UB X. This is a differential equation. Then for fixed U, we have again the trajectory for this initial point. But we can go from this x0 point here for some time t0 and stop, for example, here, because we just use this time t0. And then here we change the control. Instead of u, we take another control, for example, u0. Then with this, the ordinary equation will change and the trajectory also will change. Then we can, for example, go in this direction here. So here we use, for example, another time t1 and another control map u0. And here we use just u. And so with this time t1, we reach this point here. And from this point here, we can choose another time and another control function u, and we can change the trajectory to another direction or another. And then with this, we can try to control this state space. For example, in this case, state space is R2. And in this situation, the question is if it is possible to go from some point X to another point Y using this control U with values in the subset of Rn here. So this is the idea of controllability in this case here. This kind of system is called affine control system in our context. And if you consider this 0 and this vector also 0, we will have the homogeneous control system associated to this affine system 1. In a more general context, we can consider, instead of Euclidean space, we can consider this smooth manifold M and take this equation here, where F0, F1, and so on are smooth vector fields on M. And we have again the control range in Rm. In our work here, we will work with omega, a compact subset of Rm containing the origin of the space. We assume that for every initial state X of the state space M, in this case is a manifold, and every control function U, we assume that there exists a unique solution denoted by this phi here, and satisfying this equality here. Then a particular case, we can go back to particular case, and we can write as A of U, the sum here, and then we can abbreviate that notations, and we can got this equation here. Then we can write the affine control system in this way. And so with this, we have here the affine control system. And if you use this notation here, we can write this in this situation here. And if you consider this vector A equals 0, so we will have the bilinear control system. And the homogeneous part is just consider the vector A and the vector BI equals 0, equal the equal origin of the Rn. So the idea of this work here is related with old papers of Bonnard, Jurjevic, and Kupika and Salet. In these papers, these mathematicians study affine controllability or transitivity in connection with the homogeneous controllability or transitivity. I mean, we so the idea of these mathematicians was to find the conditions for the controllability of this system here from this system here, from its homogeneous part. For example, if the homogeneous bilinear control system is controllable, then the affine control system is controllable, or we can have an equivalence between the controllability of the affine control system and its bilinear or homogeneous part. The answer for this question is this theorem here. The affine control system is controllable if it has no fixed point in this sense, and if it is homogeneous part is controllable. This S here means the semigroup of the system. The semigroup of the system is given by, for example, if you take this, let me consider a particular case. Let's consider this bilinear system here. Then we can take N, for example, the set of the matrices A plus UB, where U is the control maps that we are considering. Then we have here the set of matrices. With this, we can consider the exponential of, for example, T K multiply A plus U K B. Then we have here this flow. This is a flow of this matrix here, or the solution of the ordinary equation with U fixed. And then in this case, we have that this semigroup system is defined by the concatenation of that exponential. Tk A plus UK B exponential Tk minus 1 A plus U K minus 1 B, and so on until exponential of T1 A plus U1 B with positivity then this S is a semigroup. And if you consider real T, not just positive T, then we will have a Lie group, D. And the controllability in this case means that the orbit of Sx is all Euclidean space or state space. But here, semigroup system means this semigroup here. And group system, we just consider real time, not just positive time. Now we have another concept. This is the positive orbit. Then the positive orbit here is given by this union, where this guy here is given by this equality here. So is the reachable points from x up to time t. What means this? Means one element y in this positive orb up to time t from x is, so here we have the point x, and this set here is the set of every y that we can reach from x using time between 0 and this capital T and the u in the set of piecewise constant function. Then, for example, we have here this another point that we can reach. Here another point that we can reach. And then the subset here is the point of M that we can reach from X. And the similar, we have the negative orbit. The definition is very similar, but here we are just considering the points y in M such that we can reach X from Y. So in some sense, is the negative orbit. Another concept that we need is the concept of locally accessible. So we have that the system is called local accessible in X if we have that the interior of this orbit here are non-empty, the interior of the negative and the interior of the positive. And it is called locally accessible if this holds for every x in M. And we say also that the system satisfies the accessibility rank condition if you have this equality here. The dimension of the subspace, LA, is equal to the dimension of the manifold, where this subspace here is the tangent, is the subspace of the tangent space of M in X, corresponding to this vector F0, F1, and so on, evaluated in X. So now we have another concept, that it is the concept of equilibrium point. The equilibrium point of a affine system, that affine system, is the point XU such that we have this equality here. And here we consider that for every U in omega, there is at most one solution for this equation. And we have also the equilibrium set. The equilibrium set is the point of Rn, such that we have this equality. And the E0 is the point of Rn, where this equality here holds for u in the interior of omega. And the idea of this work here is not to study the controllability, the global controllability. I mean, we don't, in this work, we don't care about the notion of global controllability. So global controllability means that given 2 points x and y in the state space, there exists a concatenation of the solution, or there exists an element of the semigroup of the Lie group of the system, such that we can reach y from x using these elements of the semigroup of the system. So we don't care about this global controllability. Our idea is to study local controllability in the following sense. Local controllability here means that if you not have global controllability, if we don't have this property for every 2 elements of Rn, we can try to find, if you don't have this, we can try to find a subset here in Rn where we have this property. So for every 2 points here, inside this subset here, we can go from x to y using the elements of the same group of the system. Then we have, in this case, the concept of control set. More specifically, the control set is a subset of the state space, such that for all elements of this subset, there is a control function u, such that the solution from x evaluated in u will be in D for all positive t. And the second condition says that for all x in D, we have that D is in the closure of the positive orbit. And the third condition is just a technical condition, says that the maximality of these 2 previous properties. And we have that a control set in M is called invariant control set if you have the equality between the closure of D and of the positive orbit. Then we are, our interest is in this kind of set here, this control set. So we can note that from these 2 properties here, we can say that this control set, this set D has the property that given 2 elements in the interior of D, we can find a concatenation of the solutions that we can reach y from x using positive time. And another idea of this kind of concept is the chain transitivity set. What means chain transitivity set? Is similar to this control set, but we just want that we can go from x to y using jumps. So, for example, we would like to go from x to y inside a subset here, using it, it's allowed to use jumps. For example, we can go here until this point and take a near point here and go to another point here and take a near point here and go until the another point. And so using this kind of jumps, we can reach Y. And this jump here is given for some distance, epsilon distance. In the control set, in this definition, the previous definition, we need to go from X to Y directly. And in chain control set, it's allowed to do this using this kind of jumps. Then to define better the chain control set, we first define what means a epsilon t chain from X to Y. This chain is given by n, this natural number, by these elements in M and these control functions in U, and this positive times here, greater than capital T, such that the first element x0 is equal this fixed x, and the last element xn is equal this fixed y. And with this, we must satisfy this inequality here. We can do this, but with the distance between the previous point and the next one is small or equal epsilon. So this is the idea that I put in this picture here. Then if for every epsilon and capital T positive, there is a controlled chain from X to Y, then the point X is chain controllable to Y. And the concatenation of two controlled chains again implies a controlled epsilon T chain. And in analogy to control sets, chain control sets are defined as maximal regions of chain controllability. So this is the idea of chain control set. A set E in M is called a chain control set for a control system if for every X in E there is a control U such that the solution phi of txu is in E for all t, and for every two elements X and Y in E, and epsilon and the t greater than 0, there is a controlled chain linking X to Y. And the E is maximal with respect to these properties. For example, every equilibrium that we defined previously and every periodic trajectory is contained in a chain control set. And the chain control set are closed, and for locally accessible system, every control set with non-void interior is contained in a chain control set. Every control set is contained in a chain control set with these conditions here. Now, we have this notion of chain transitive set. So what means chain transitive set? A chain transitive set is a subset of the state space M, such that for all X and Y in this subset, and for all epsilon and capital T positive, there is and there is a chain from X to Y given by this natural number, this sequence of elements in M, this sequence of times with this property here. The jump must be small or equal epsilon. So we can go from x0 to x1 near to x1, for example here, and the distance between is smaller than epsilon, and then we can take this and go to another point near to x2. I mean the distance between this small or equal epsilon, and so on until we can reach the element, the point Y. So now we have here some technical definition, the definition of non-hyperbolic affine control system. Then this definition here, for this definition, we take a periodic differential equation where, given by this equation here, of course, and where we have the fundamental solution of this equation 5, given, I mean, what means fundamental solution? This is the solution that satisfies this equality here. And then we say that the affine system is hyperbolic if the number 1 is not in the spectrum of this fundamental solution for all tau periodic U, control U, in this set of control functions. Otherwise, we have that the system is non-hyperbolic. The importance of this definition here is just to guarantee that such system, for example, x point equal ax plus ubx plus ub is to guarantee that this system here has an unbounded control set. For example, if the system is in R2, this kind of property, previous property, guarantee that the control set here is unbounded. For example, something like that. Then we can change this this property or this definition by this hypothesis here. Suppose that the system have an unbounded control set. For example, here is the control set. Non-empty and unbounded control set. Then let me give here the geometric idea of this work. The geometric idea is the following. If you take R2 or state space and the control set given by, for example, this cone here. This is the control set of the affine system ax plus small a plus ubx plus ub. So the property that we have inside D is that we can go from every point x to every another point y in D. So this is the idea of the control set. Then suppose that the control set here is unbounded. Then we can lift this system here in the following way. Take the matrix A here, for example, matrix 2 times 2, and take here the vector A. This is a vector of R2, and here the number 0 and the number 0. Then we will construct another system given by this equation here. Now we take the same U and we take B. B is here. And I will put in this column here, I will put the small b, the vector small b, and the number 0 and the number 0. In this case, note that we are in R2 here. Product xz. Then we construct the new system. This system here is a bilinear system. For bilinear system, we have a better theory and more result about control set and controllability than a fine system. Here we have a fine system, and here we have a bilinear system. Of course, this system here are now in R3 because this element X is an element of R2. And this element here is element of the straight line. Then this new system is in R3. But the dynamics of this system is just in this plane here, in this embedding of R2 in R3. Because note that here we have 0 and 0, so the dynamics in this last component here does not exist. Then what we have? We have that this control set D here have one copy in this red plane here. There is one copy here. Then what we do now? Now we take from here, just remember that from here to R3 we have some kind of lift, and now from this R3 we have some kind of compactification. We can take the compactification, the projective space, in this case will be the homogeneous space P, P2, and again we have that this cone here, this control set, will have some kind of copy here when we take this compactification. We can prove this, and geometrically I think that it's clear. Then, for example, we can call D1 this guy here, and we call this new cone in this projective space, we call as PD. So we note that if you project, or if you separate P2 in its boundary. So what we are doing here, we are excluding, in some sense, P1. Here I have some abuse of notations. We are excluding P1. Here is P1. Then we have one map from here to here. Note that this set here, PD, this set here, will have in the boundary of at infinity, we will have some part here because we disconnected this. Then in the infinity, in the boundary of this set here, PD, we have this guy here, D0. I will call D0. And in this construction here, we have that this system, when we do this kind of construction, this system here, we can prove that this system in P1, in this projective space, is just the homogeneous part of original system. So the idea is trying to relate the control set of the affine system with the control set of its homogeneous part using this construction here, this projectivization. So let me put it in a more clear situation. Here I will consider a very special case. Take this very simple control system. This is a linear control system with control range in Rm. And we will assume that this control system here is controllable if you take U in all Rm. So assume that the system without control restriction is controllable. This means that this system is controllable if you do not restrict to a subset. Then we will denote by GE the real generalized eigenspace for an eigenvalue μ of A. Then we can prove that E0 is inside the control set D. This is the control set of the linear system. And this control set is inside this sum here, where E0 is this direct sum here, is the central spectral subspace, and the K is the sum here with real part of μ of this eigenvalue negative. Then we have this this set here, and the F will be a subset of this subspace here. This is a result that we can prove as a corollary of some result of some type book. But what we have from this? We have that this control set is bounded if and only if E0 equals 0. I mean, if A is hyperbolic. So this is the idea to take A non-hyperbolic. If the system is non-hyperbolic, then we can prove that the control set is unbounded, and then we can do this. Because note that it is not possible to think in this context if the control set D is bounded, because it does not make sense to study the boundary at infinity of bounded subset. Then, in this case, in case of linear system, the result that we get is the following. First, if we have a non-hyperbolic system, we embedded the system in a homogeneous bilinear system. This is this kind of lift here that I said. And so in Rn plus 1. And for the corresponding control set, PD1 in Pn, in the compactification of Rn plus 1, we find that the boundary at infinity satisfies this equality here. What means that the boundary at infinity of the control set, the behavior of this control set here at infinity, is given by just an element of the plane, the zero plane, the plane parallel with x1, x2, xn in the origin. I mean, let me draw a picture here. In this case, if the control set, if the system is non-hyperbolic, then the control set is unbounded. So we have some kind of behavior like that. And the boundary at infinity of this control set here, this is D, will be some part of Pn minus 1. So this is the idea of projective geometry. We have the plane here, and we have that this behavior in the infinity will touch this plane here, because we can write the projective space as the union of P n minus P n minus 1 union with P n minus 1. Then here we have Pn minus 1. So in this case, we can compute this and prove that the boundary at infinity of the control set D is a maximal invariant chain transitive set for the induced flow in Pn0. So this set that we will have here, the boundary at infinity of the control set, the boundary of infinity of the control set, have the property that we can go from one point to another point using jumping. This is the idea of maximal invariant chain transitive set. But the problem here is to generalize this situation. Consider not a linear system like x point equal ax plus ub, but consider now system in more general context, ax plus this vector here plus ubx plus ub. B also is this small b here is a vector in Rn. In this kind of system, the computation is more complicated, of course, and we may replace the maximal chain transitive set in the projective space by a maximal chain transitive set of the control flow associated with the homogeneous part. So we have that in this case, we prove that the control set here in Rn, the unbounded control set, the boundary at infinity of this control set will be in P n minus 1 here, and this subset of Pn minus 1 will be the boundary at infinity, have the chain transitive property. So will be the maximal chain transitive set for homogeneous system, because here I consider the affine system ax plus a plus ub x plus ub in Rn, and here in Pn the system will be x equal ax plus ubx, and this green set here will have the property that we can go from one point to another point by jump. We expected when we begin to study this, or we thought that this green set here will be again a control set, will be also a control set. We hope that this green set here should be also a control set, but not. We can prove that we cannot go from some point to another point directly. We cannot prove this, but we can prove that we can go from some point here to some point here using that kind of jump. This is the idea of chain control set. And this is not difficult to, in some sense, to believe, because when we take this system here, x point equal ax plus a plus ubx plus ub, when you take this, and if you consider x with a very big distance from origin, I mean the norm of x is very, very big, then this vector, constant vector here, does not matter in the dynamics, neither this one here. So if you take, or if you consider the norm of x going to infinity, then this small a and this small b doesn't matter in the behavior of the system. And so this is the idea. And here in this picture, we have that picture that I draw. Here, for example, we have the control sets. In this case, 2 control sets. We have this example in the paper, we have this 2 control set, and then we lift this to R3, for example, and then project in the projective space P2, and this control set here will be this control set here, this here, and the another side of this projective space, the other. For example, here D, and here D1, and the C here, and so in other side of this projective space we have C1. And in the boundary at infinity we have here P1, a subset of P1. Will be this guy here, and the D1 is this here. So I think that I will stop here, and thank you very much. Let me try to see everybody again, what I need to do. Maybe. Why cannot I see you? Maury, I will stop here, but how can I see you? Oh, strange. Ah, okay, just stop sharing. Oh my God. Thank you very much.
Thank you, Alexandre. Does anyone have a question or comment? Oh,
No, thank you.
There's a-
It's too late for questions.
Yes.
Already, right?
In Italy, at
Early in
least.
the morning. But thank you.
Yeah.
It is
Okay.
great time.
okay. Thank you, Alexandre,
Thank you very
for
much.
participating.
My pleasure.
Then this is the last talk for today. We'll be back tomorrow at the same time. Thank you, everybody, for participating today. And then
Thank
I'll
you
see
for your attention.
Welcome.